Math 8, Unit 2, Transformations, Lesson 6, Part 1, Similarity, Introduction. How do you know if figures are similar? Now, one way you can tell, you should be familiar with, is to measure the angles and see that the angles come out the same. For example, if this were a 70-degree angle and this were also a 70-degree angle, and these had the same angles, this other angle would have to be 40. If the angles are all three the same, that will tell you they're similar. There is another way that you can tell that these two triangles are similar. If you measure the lengths of the sides, so you could use a ruler and measure the length of the side, that's 5.3. Actually, just in the interest of time here, let's say that I measured these previously, and this was 5, this was 6, and this was 6. Measuring these two are each 3, and this one's 2.5. So, if you measure their lengths, then you can use that to determine if they are similar or not, because they'll be proportional. If we take each side and compare it to its respective side, so we can compare 6 to 3, we could compare this 6 to this 3, and we can compare this 5 to this 2.5, and if they are proportional, then they're similar, which 6 to 3, 6 to 3, 5 to 2.5, those are all twice the denominator, so they are proportional. That is similar. So we can tell similarity based on angles or based on sides, if angles are the same and if sides are proportional. So figures that have the same shape but not necessarily the same size are called similar figures. Triangles ABC is similar to triangle DEF. And there actually is the statement, the similarity statement. Notice that the similarity symbol is like the congruent symbol without the equal underneath it. That means it is similar in size, but not necessarily equal in size. So two figures are similar when their corresponding side lengths are proportional and their corresponding angles are congruent. We'll be putting this in the notes later on. How do I find missing lengths then? Well, if they're similar, then their sides are proportional. We can do this two ways. Way number one is to use proportions. I guess these are both using proportional reasoning. If I compare 6 to 3, I should get the same thing as if I compare 5 to x. I can cross multiply and solve here. This is 6x equals 15. I would divide by 6, and I'd get x equals 2.5. So 2.5 centimeters would be the answer for x. Okay, that's using proportions. In certain situations, it is quick and easy to use scale factor. So the second way you can do it is scale factor. Now for scale factor, I am trying to get to x. I need to go from 5 to x, but I can look at my other sides to figure out how that's done. Going from 6 to 3 using multiplication or division, I can divide by 2. So the scale factor here actually is 1/2, multiplying by 1/2. That's the same as dividing by 2. So I can go from 5 to x by dividing by 2, and that would give me 2.5 centimeters using scale factor in division form rather than multiplication. It's actually 5 times 1/2. Okay, right here we can use either scale factor or proportions. Notice what we have in common between them. The 10 will map to 15. Do we know 10 times what gives us 15? We actually should know that. If we multiply by 1.5, that will get us from 10 to 15. So we can, to get to the question mark, that comes from the 8. So I would do 8 times 1.5, which equals 12 to get that. Again, this can be done another way. We could have compared 10 to 15 the same way we compare 8 to 12. Not 12. We wouldn't know it's 12 yet. We'd compare 8 to x. Then we cross multiply. 10x equals 120. 8 times 15 is 120. Divide by 10 and you would get x equals 12. Which rectangle is similar to rectangle 2? Now rectangles, they all have the same 90-degree angles all the way around, so we're not going to be able to use angles here to tell similarity. We are going to have to use proportions. So within each rectangle, let's go ahead and compare its height to its base and see what we come up with. So comparing its height to its base, this rectangle is half as tall as it is wide. This one's a third as tall as it is wide, and this one's half as tall as it is wide. This has the same proportion within it. So if I compare the proportions between, it will end up actually working out just fine. If I compare 6 to 4, I'll get the same thing as if I compare 3 to 2. And that is true. This one would work. Cross multiply, you get 12 equals 12. They are proportional. The triangles are similar. Find x. Okay, we can do this with either scale factor or with proportions. Do we know how to get from 6 to 9 using multiplication? If we do, then we can do the same multiplication to get to x here. It is times 1.5, so we could get x equals 12 that way. Or let's look at doing it with proportions. 6 compares to 9 the same way 8 compares to x. Now if we cross multiply here, we get 6x equals 72. If we isolate the x, we get x equals 12. Same answer, different method. Okay, next. 6 to x and 9, 6. So 6 goes to 9. If you know how to get there directly with multiplying by 1.5, you can use that. But we'd actually have to divide by 1.5 to go backwards, because x times 1.5 will be 6. And we divide to go back. And it looks like x would have to be 4. This one might be better to do with cross products. 6 compares to 9 the same way x compares to 6. And if we cross multiply and solve on this one, we would just divide by 9. And we do get x equals 4. And maybe we didn't have to think as hard about it. Okay, next. Let's look at number 3. This one's actually pretty good for scale factor. If I go from 7 to 14, that's times 2. So I need to multiply by 2 here. 12 times 2 is 24. So x would be 24 centimeters. Again, this can be done with cross products. 7 compares to 14 the same way 12 compares to x. If we cross multiply, 7x will equal 168. Divide both sides by 7, and x equals 24. Okay, that's the end of part 1.